Hello, everybody. Hope you are well. I'm here to talk about optics. So I realize that not all of you are working with optics on a day-to-day basis. I have a couple of topics that I want to talk about. So first one is the infotainment part. I want to take us a little bit back. This is, after all, a celebration. 20 years. It just happens so that in 1996, and I promise I'm not going to take you all the way back to 1996 because then we have to talk about all sorts of embarrassing things that have happened over the years. But in 1996, when Netnod was actually founded, I was offered a job at Ericsson to become the PLM, product manager, for a brand new technology that we were developing back then. It was called wavelength division multiplexing. So that's when it started. So Netnod, I guess it wasn't a company in 96, but the operation started, is as old as, WDM, and as old as me. So I've seen all of the technologies that have come and gone, so I think it's worth to touch base on a few of them before we move into the maybe more interesting content of the presentation. AI and the new data center architectures that we are expecting, that has already been built. What is the impact on the optics? And I have to be very clear here, I am not a data center architect, I am an opto nerd. And when I talk about a data center architecture, I will talk about the optical piece. I also want to talk about how the coherent optics is streaming into the data center world and into the operator networks, and very specifically about technology where we can see how IP, layer 2, all of these technologies kind of blend in with the optical piece rather than building an optical transport network that is servicing the IP layer and other layers as it used to be, something we call IP over DWM. That's the specific thing that I want to look at a little bit. So let's start. What would I have been talking about if I was here 20 years ago? Because this is the 20-year anniversary. I'm not sure how many of you recognize these abbreviations. This was the hot topics 20 years ago. OTN, Optical Transport Network. ASON, Automatically Switched Optical Network, and GMPLS, Generalized MPLS, a control plane technology. Luckily, these things are now fading away. OTN, maybe a lot of you know what it is. Today, you probably view OTN as a framing protocol where you have a good forward error correction algorithm. You probably have some data channels for in-band management, and you may have room for other things like layer 1 encryption in the case you need that. But back then, OTN was a completely different beast with a complete architecture on how you should build a network to ultimately mimic something that I think is way better suited for IP technology, as an example, to take responsibility of, such as dynamic bandwidth allocation. Let's assume we have something happening on one side of the city and we want to allocate services to an arena or whatever it might be, or a show. That's something that's happening every day in a routed network, and it's not happening that often in optical networks. But that was the idea with that architecture. So OTN survives, and I will come back to OTN a little bit. The other two are pretty much gone, and the reason why they are relevant to bring forward here is that this is precisely the opposite of what I'm going to talk about, namely how do we get IP and routed technologies closer to the optics to build a more integrated solution out of it. IP over DWM, or IP over glass, or whatever you want to call it. So that's the reason why I want to bring it up. Looking at optics, how we have followed the trend, I think most people, when you talk about the internet and how fantastic the development has been over the years, there aren't that many people out there that think about, oh, optics has played an instrumental role in this, but I think it has, no doubt. Optics has I'm saying almost kept up with Moore's law. I'm not sure whether Moore's law is relevant. Many people claim that it's not anymore. But if we use that as our reference, we can conclude that DWDM technology, something that we don't talk about that much anymore, is the king. And I will show that in a graph in a minute. DWM was enabled by this fellow in 1843. His name is Carl Gustav Molander. He discovered erbium in the rare earth erbium out in Vaxholm, a mine where it was discovered, and I think the majority of it still comes from this part of the world. What was important with that? Well, it was a rare earth that made the erbium-doped fiber amplifier possible, meaning we could take light, amplify light without altering the ones and the zeros in there. The only thing we did was to add noise, but that we can calculate and we can manage it and we can plan away noise. So erbium was kind of the prince in all of this. Without the erbium-doped fiber amplifier, DWM would not have happened. Before that, it was point-to-point links between SDH cross-connects and similar machines. Nowadays, everyone is talking about coherent technologies. So, and here, that crown is a queen's crown. I have no idea why. And of course, this is also a Swedish perspective because we happen to have a king and a queen. But if you have a queen and a king, I guess it should be the other way around. Coherent technologies has developed vastly over the past years. We're expecting it to continue to develop for a while longer before we can't see anymore. So I guess the horizon is there at 1.6, 3.2 or something terabit, where we kind of have a notion of how it's going to be done. Of course, it will develop beyond that, but at least I haven't seen any visibility of that yet. So I'm saying that DWM is the king, and I plotted Moore's law versus the development of the capacity in an optical fiber in a practical sense. It's not 100% correct because I used 5 years intervals. How much capacity did we have in 2000 versus 2005, etc. And you can see one big leap, and that's here. This is when DWM actually happened. So all of a sudden we had 40 or 80 or whatever times the bandwidth of an optical fiber. And ever since then, with the advancements of the modulation technologies, of course, the bandwidth has gone up dramatically. We're no longer 10 gig. We're 100 gig, 200 gig, 400 gig, 800 gig, and emerging 1.6 terabit per wavelength. So that's, of course, a massive development. But still, you can see that we're kind of tapering off here. And the question is, do we need more in the future? I don't know, but maybe. But DWM, a very, very important technology. One of the topics that I had in my overview was AI and what AI data centers is doing to the optics, and I'm going to talk about that. I just want to point out that if I had been here 9 months ago, or probably 12 months ago, I would have said that we don't know whether AI will affect the optical industry or the optical business or the architectures that we use. Some people on the planet probably knew, but certainly I didn't, and many people like me didn't. And I think now we can conclude that yes, it is affecting the optical industry. I'm going to talk about how, and AI is really leaving the data centers in a very obvious way. So that's good for us who work with optics, and I guess good for everyone who works with AI, because it's impossible to monetize anything that sits inside a data center only. That's number one I wanted to talk about. Number 4 on this picture, you see the little chili fruit there. That's a quote from a guy called Gary Smith. He's the CEO of Ciena Corporation. If you don't work with optics, you may not know who Ciena are. They are kind of the leader, the biggest one in the industry, selling more than anyone else, having very high-end solutions. And he's saying, you know, optical is cool again. It has taken 20 years, but it's finally cool. I don't feel that way. In my mind, it's been cool all along, to be perfectly honest. And I think all my colleagues, if you go ask them, do you work with the cool technology? For sure we do. But this guy, he's been sitting there for 20 years waiting for it to be cool. And he's been the CEO of Ciena Corporation all along. So that's kind of mind-boggling to me. But anyway, good for Gary, good for the rest of us. We are working with the cool technology. And if you're a beginner and you want to go work more with optics, now is a good time because it's really happening again. Okay, so I'm going to turn to the first kind of real topic now and talk about AI impact on the optical network. And let's start with the architecture of a modern GPU, kind of NVIDIA-enabled data center. What do they look like and where do we find optics in this? So you can see the architecture on the right. Just for reference, you have way right, you have a normal spine leaf kind of architecture with servers connecting up to switches in an any-to-any fashion and so on. The new thing, and you can hardly see it here, and the contrast is not great, but what you see down here is kind of the back end of the AI-enabled, the NVIDIA-enabled data center, where you have all the GPU to GPU communication going on. That's completely new. Is this big or is it small? Well, if you look into one of the bigger AI data centers of the hyperscalers, you will notice that in this area of the network, not leaving the data center, just an any-to-any connectivity between GPUs, you will find that there are several 100,000 400 gig and 800 gig connections there. So that's huge. Hyperscalers are called hyperscalers because they are hyper, and this is another area why they are hyper. This is an area where we've seen some innovation and where I expect there will be more innovation. Cost is of course key. We're talking about several 100,000 connections at 400 or 800 gig. That's expensive stuff. We see new technologies, not a new technology, but certainly technology such as InfiniBand offering way better latency than many other things. That's probably why NVIDIA acquired Mellanox a few years ago to get access to the InfiniBand technology. This is also where you see the co-packet optical development happening. Co-packet optical is when you, by using silicon photonics, you put it on the same chip as the switch. So it's actually a switch that has the transceiver's optical technology closely located on the same chip, effectively, to get efficiencies in power, space, latency, and all of the stuff that you expect to be important in this part of the network. This is also where we're seeing new stuff coming out. The latest one that people talk about now is something called EL optics, EL SFPs, so it's external laser small form factor SFP, meaning that you maintain the DSP part of the interface on the silicon itself, close to the switch, but you break out the actual laser component, because that one is probably the component that's going to age here, where you can expect to have a wear out period and you may want to replace it. So you have, instead of having, like you're probably used to, because although not all of you work with optics, you are using optics, nearly everyone here, and you are plugging SFPs and XFPs and QSFP DDs and so on, probably. So instead of having a full optical interface with all of the electronics, all of the optics in one, you only have a laser. So those are the type of things that are happening in that part here. It's all about cost, latency, and power draw, because it's massive. It's way more connections. I don't know what the ratio is between back end and front end, but it's probably a huge difference here. And in the more conventional front end where servers are communicating with each other. And the last part of this is, of course, the data center to data center communication, which is today nearly all about coherent optics. So why is this going on? Well, there are multiple reasons. The normal ones are security, redundancy, lack of space and power, obvious. And of course, when you build these gigantic data centers with a lot of NVIDIA technology, you realize that you will have grid problems. You know, you simply cannot get enough energy to a particular location. So you have to start distributing, and that's a big thing. So from an optics standpoint again, what is the impact here? And I think these are things that people talk about. I think we have proof of nearly all of them. You know, bandwidth is growing. How much is it going to grow? I don't know. In the WAN I'm talking about now, is it 10, 20, 40, 50%? Well, it remains to be seen. And I guess someone like Netnod will be one of the first to see what the answer is, because you can measure it on a day-to-day basis, I expect. Distributed AI fabrics is something that was not talked about a few months ago or even a year ago. It's happening now. I will show you on the next slide what NVIDIA themselves are saying about distributing AI fabrics. It is happening already today, probably not over very long distances because of latency impairments of the older NVIDIA technologies. But it is happening, and it's done over fiber, and all fine. Enterprise inferencing is another topic that I'm hearing a lot about. When are normal companies going to start doing fine-tuning of their models in their own GPU clusters? Are they going to continue to rely on the hyperscalers? Is that going to become too expensive eventually? And do you want to build your own in-house architectures to do that? Regardless, both of those means an awful lot of data center to data center communication that needs to happen. So distributed, and of course for us as a company, you know, just starting to collect an awful lot of data, doing day-to-day analysis and such is an opportunity for us to work with. So distributed AI, I said it has happened over shorter distances, and this article came out 22nd of August, so not long ago, from NVIDIA, where they are kind of talking about their Spectrum SGS technology. I don't know that much about it, but it's obviously, if you listen to Jensen Huang here, the founder and CEO, what he's talking about, well, he's talking about distributing and building what he refers to as giga-scale AI factories across many data centers. He is talking about within cities, I believe, somewhere, and within regions and between countries even. I don't know whether that's practical to have that much of latency put into the equation. Maybe a region is quite okay from a power feed standpoint and so on. Remains to be seen. But certainly it is happening. So more and more coherent technologies in data center interconnect applications. That's going to happen. That's obvious to me. So looking at data center interconnect and coherent optics, how much of it is used and in what way it is used, and what are the applications that we are generally talking about. And here, in the concept of data center interconnect, this could be really anything from a hyperscaler to a dog food manufacturer in Luleå in northern part of Sweden. There are so many people who are either building their own data centers or co-locating in data centers, building replication facilities outside, needing to build a data center to data center optical network. And I think only Smartoptics, we probably get a new customer every week doing this. And it's really anything from hospitals, schools, as I said, dog food manufacturers. We actually have one of those that's why use it? Car part manufacturers, banks, whatever. So there's a lot of it. And in this world, what are we talking about? Well, we're talking about connecting a couple of data centers. If it's a bigger case, it may be 4 or 6 or 12 or whatever within a city, but it's typically not a large problem. Very high adoption level of IP over DWM, meaning people are taking the coherent 400 gig optics, they are putting it straight into the routers and switches. Is that minutes or seconds? Perfect. I need 9.5. He said 10 minutes. Right. And they are running it over way more simple optical networks than they would have done 5-10 years ago with really complicated machines with large needs for configuration, etc. So really high adoption level here. There's been a form factor battle that I'm sure every one of you have, well, those of you working more closely with optics have taken notice of. Is it going to be the QSP-DD or the OSFP? And I think on 400 gig, it's obvious that QSFP-DD, that form factor, won. When we move into 800 gig and beyond, I think it's going to be a little bit different. Rumors and what you hear from the hyperscalers, they're all going to go OSFP because it's simply a better technology. You can cool more, you get higher faceplate density on your switches, so OSFP is great. If you talk to operators, they will say, QSP-DD is better because we get backward and forward compatibility between generations. So maybe the world is going to split up here between two different form factors. OSFP as a form factor was really only one of the hyperscalers and one of the switch manufacturers in the past for 400 gig. And very, very large volumes deployed. So this is, the green one is the number of 400 gig. This is data from one of the analyst houses. So it's 200,000, 200,000, 200,000. So it's about a million 400 gig ports out there. And you can see that 800 gig, again, shitty contrast, but starting to have a meaningful impact on networks from next year. And 1.6 terabit is still a few years out. So what about CSPs or operator networks? Well, very slow adoption rate for IP over DWM. There is a high interest, regardless of who you talk to, they have an interest to talk about it. How can we make our networks more effective, efficient? Can we utilize the same type of technologies that you are using in the data center world? For sure you can, but there are problems in an operator network, and it's both performance and operational challenges that you have had to deal with. So when we talk about performance, yeah, so I see it's the old slide. I made a new one for this, sorry, but it's good enough. So when 400 gig came out, it was the OIF standard, 400 gig only. Not too many application modes, basically 400 gig from one point to another, pretty weak forward error correction. You could really only run it in a point-to-point fashion. Obviously not a great technology for operators. Quite quickly after that we got the CR Plus technology, much better, more application codes, more use cases, and suitable over things like ROADM-based networks, reconfigurable optical networks. And what we're expecting now is 800 gig to come out, or it has already come out, with something called probabilistic constellation shaping, where we can start using the states in a constellation diagram that are optimized for what we want to do based on statistics. So then all of a sudden you have a pluggable technology that can do up to 800 gig, and it can do anything between nothing and 800 gig. So here we have a new complexity to take into account. That's the number of application codes, combinations of baud rate and modulation format. I think in the one we are using, it's about 70 different use cases for one transceiver. So that's clearly a new level of of complexity. Here we have modeled the network from the very northern peak of Sweden to the very southern peak of Sweden. ROADMs, line amplifiers, Raman amplifiers, all of the optical mambo-jumbo that you can think of. Pretty standard stuff though. And we modeled one of these 800 gigs running in 400 gigabit mode. And you can see that the margin, although it is 0.0 dB margin to run this, it is quite possible to do it. So 2,000 kilometers using a pluggable 400 gig transceiver. That's pretty fascinating. The other challenges, organizational challenges, that's a simple fact that in a CSP, it's typically one team working with the optics and one team working with the routers and switches, and they rarely talk to each other. Worst case, they think that the other team is an idiot or idiots in plural, and that is, yeah, maybe that's the case, I don't know. Anyway, that's difficult to deal with. I think I have some ideas. The other one is management, because if you are responsible for the optical network and someone starts shooting wavelengths through your optical network, that's not going to be a positive discussion with your manager when that channel has taken down 4 other channels and you had nothing to do with it. So, and you can go out there, we have this system that we're looking at out there where you can look at the concept. This is a tip concept that we have implemented into our network management suite. It's based on routers being able to talk native open config, where we can kind of associate a router port with the optical network, get all the performance data, and make everyone happy. So solving that management challenge. And here is a link to an event that was given by TIP. We're also participating in a study that's happening down in the Telefonica labs down in Spain to continue to develop this concept forward. How do you take care of the management problem involved in IP over DWM? So quite possible. My summary is data center world, done and dusted. It's very easy to run these type of networks, and the complexity involved in IP over DWM is fairly low. In operator networks, okay, slower adaptation time and rate, but certainly very possible. And there are a few tricks here that we can use to help out. Thank you so much for listening.
We have a minute or two for questions, if there are any questions for Magnus. Okay, well, you can find him at the Smartoptics stand in the coffee break or at the social. Please join me in thanking Magnus for a fantastic presentation. Thank you so much, Magnus.
Thank you.